Hey everybody, welcome to chapter 16 on one-way analysis of variance, also called ANOVA. So this is a really useful technique. It's a statistical analysis that helps us compare group means, so means of some variable, some outcome variable, between more than two groups. We have seen independent samples t-tests so far that can compare the means of two different groups on some kind of dependent variable. Well, now in real life, sometimes we have three groups or four groups or five groups that we're trying to compare in terms of some variable like anxiety or extroversion or happiness or something between multiple different groups. And this is the test that lets us do that. All right, before we dive in, a quick review question. If I want to know whether people in Texas like barbecue more than people in Colorado, what kind of test would I use? Well, it's not going to be a one sample t-test. That's about comparing one sample's mean to a population mean. It's not a paired samples t-test because here we're talking about people in Colorado versus people in Texas. So those are two different groups of people. So it's going to be an independent samples t-test where the independent variable is where you live, which has two levels, Texas and Colorado, and the dependent variable is how much you like barbecue. Your book starts off with an example where we're asking students which textbook format is most preferable. And we've got three different textbook formats. We've got the traditional paper textbook, we've got a standard electronic textbook, and then we've got an interactive electronic textbook that asks questions and has quizzes and things as students are reading each chapter. So our independent variable here is going to be text format, and it has what we call levels, three different levels. So far this whole semester, we've only been dealing with things that have maybe two different levels. For example, in the independent t-test, you might have a condition that has two different levels, that you're comparing some control group to some experimental group. Well, now in ANOVA, we've got three or more levels in that independent variable. And so the three levels here, the independent variable of text format has three levels, which are paper text, standard electronic, and interactive electronic text. And we want to compare the dependent variable, student satisfaction ratings, between each of those different kinds of formats. Well, this is kind of a problem. We don't know how to compare three or more different groups all at the same time, but that's what ANOVA helps us do. So I should have backed up and said analysis of variance is the type of test that would benefit us here in this type of situation. We shorten analysis of variance into ANOVA, and I'll be using basically that acronym for the rest of the chapter and beyond. ANOVA is really super common. We use it all the time in psychological research. It can be used in both between subjects and within subjects designs. You can have more than one independent variable. So if you had two independent variables, that would be a two-way ANOVA. If you had three independent variables, you'd have a three-way ANOVA. This chapter, though, is focusing on a between subjects design with one independent variable, although that independent variable is going to have three levels. And therefore, we call it a one-way ANOVA because we just have one independent variable. Regardless of how many levels it has, it's still a one-way ANOVA because it's just one independent variable. So in this example, we're probably going to grab a large group of students from some kind of population, but then we're going to randomly assort them into one of three different types of conditions, right? We'll have one group of students that only uses the paper text, one group of students that only uses the standard electronic text, and one group of students that only uses the interactive electronic text. Now, after we actually have them use these different versions of the texts, they could technically now belong to different populations, and that would be demonstrated if we actually find significant differences between means in terms of their satisfaction ratings amongst these different kinds of text formats. Now I want to draw your attention to the hypotheses stated underneath this diagram, and it says that the H sub O, that's the null hypothesis, is that all of these means, the mean satisfaction ratings between each of these student groups, is identical, meaning they're equal to each other, right? So there's no significant differences between the means in terms of satisfaction ratings between these three groups. The H1 alternative hypothesis is that at least one of the population means is significantly different from the others. So again, the null hypothesis in one-way ANOVA is always that all of the population means, or the group means, are equivalent to each other. But the alternative hypothesis, you could take it in one of many, many different possible directions, okay? When you have three or more groups, well, now you could say stuff like, I think one of these means, one of the group means, is significantly greater than the other two or the other 5 groups, depending on how many levels of the independent variable you have. You could say, I think that all of the means, all the group means are going to be different from each other. You could say, at least one of the group means will be different from the other groups. You could make it even more specific. If you have 3 groups, I think that group 1 and group 2 will have a higher mean than group 3, but not different from each other, right? So there's a lot of different ways you can go in terms of alternative hypotheses. In terms of our example of student satisfaction ratings of different textbook formats, we don't really know, so we'll just go with this last idea here. At least one of the populations or one of the group means will be different from the others in terms of student satisfaction rating. A quick note here, we don't actually use one-tailed or two-tailed hypothesis testing when we're talking about ANOVA because we have more than 2 different groups. We're comparing 3 or more sample means. So that's just a quick note that that's something we have to worry about when we're talking about z-tests and t-tests, not something we have to worry about for f-tests, which is what ANOVA uses. All right, so we've got to talk about a brand new distribution. We've talked about Z distributions, normal distributions, and T distributions. Now we're talking about F distributions. And this is a whole family of distributions. There's different kinds of F distributions that slightly change the shape of the distribution based upon 2 different degrees of freedom, which we'll get to in a bit. But basically, the F distribution results from comparing 2 variances to each other. And you're probably thinking, what are we talking about 2 variances? We were just talking about comparing 3 or more means from different populations or different samples. Well, it has to do with how the math works out. We wouldn't actually be able to calculate a statistic using mean differences of more than 2 groups because there'd be a lot of mean differences. You'd have to calculate the mean difference between group 1 and group 2, group 1 and group 3, and group 2 and group 3. And it doesn't really work out. And so instead, we take the 3 different samples or 3 different conditions in our case, and we can translate that into 2 variances as opposed to 3 means. I'll show you how to do that in a second. Anyways, if you do that and calculate an F statistic, it creates the F distribution, which is the distribution of all possible F values for a specific combination of degrees of freedom. So now we have 2 degrees of freedom to worry about. So this is what an F distribution looks like. And remember, there's a lot of different F distributions. They'll all look slightly different based upon the 2 different degrees of freedom that we're going to be talking about in a second. But here's sort of the basic gist of what they look like. You'll notice that they're right skewed. They have a positive skew to them. And that's because they're comparisons of variances, and variances are always positive values. You can't have negative variances, and we'll talk more about that in a second. But you're thinking, well, it's skewed. Doesn't that mess things up? Isn't it not normally distributed now? And can't that, that doesn't allow us to use the F table because we wouldn't know. Now, all of this has been taken care of already by many, many statisticians before our time. And so you can still use an F table just like we were doing with Z tables, unit normal tables, or T tables. once you find your F critical value and establish the critical region, then you compare your F test value against that, and if it falls in the critical region, you can still reject the null hypothesis. So it's going to take the same steps for hypothesis testing that we've been doing all semester. Here's some fun facts about the F distribution. So because we use variance, like I was mentioning, instead of means, F can never be less than 0. So when we calculate an F score, which we'll do later on, it can't be less than 0. It can never equal 0 unless there is no variability in the data. So think about that for a minute, and that'll make sense once we look at some more formulas. But a nice thing about the F distribution is that an F ratio will always, or F value, F score, whatever you want to call it, will always equal 1 if there is no effect of the independent variable. So looking at the one way to calculate an F statistic, or F score, or F value, or F ratio, all those things mean the same thing, is looking at treatment effect plus some kind of error divided by error. If the treatment effect is equal to 0, then that drops out of the equation and you're just left with error over error, which is 1, right? And so the F value will equal 1 if there is no effect of the independent variable on the dependent variable. And if there is no effect of the independent variable on the dependent variable, what that means is literally, that means that the sample means are all equal to each other. So that means that the null hypothesis would be retained. So if there are no significant differences between the means of the independent variable, that is the means of the different samples or conditions we're comparing, then there will be no effect on the independent variable, and therefore F will equal 1. So that's kind of a nice baseline to get in your mind. As I mentioned earlier, the exact shape of each of the F distributions is going to depend on the sample size and number of groups involved in the ANOVA, because the F distribution actually has two separate degrees of freedom terms. We've never seen that before. Usually when you're doing like a t-test or something, there's only ever one degree of freedom term. Now with an F distribution, there's two different degrees of freedom terms. One is called the between groups degrees of freedom, and one is called the within groups degrees of freedom. And those can be calculated like you see on the right-hand side. So between groups degrees of freedom is the number of groups minus 1. So the number of groups is represented by the letter K in this case. So degrees of freedom between, in our example, there's 3 different groups or 3 different conditions. Minus 1 would be 2, right? That would give us 2 between groups degrees of freedom. The within groups degrees of freedom is the total sample size across all of the groups. So adding every person from every group together to make a total sample size minus the number of groups or conditions. All right, and just like the move from the dependent samples t-test to the independent samples t-test, where the math got a little bit more hectic and complicated, it's definitely going to take another jump up in terms of complexity for ANOVA. And so we've got to talk about some new vocabulary terms which we'll be using in the calculation of the F test. We've got our grand mean, between groups variance, within groups variance, mean squares, main effect, and post hoc tests. And we'll go through all of these things as they show up. So here's what we're ultimately after. Okay, we're trying to calculate an F ratio or F score, F statistic, to ultimately compare to some cutoff F critical value to determine whether or not we can reject the null hypothesis. Well, to calculate that F statistic, we have 2 potential formulas that are the same thing, and it can be shown mathematically that these are the same thing. But we'll probably be going with the bottom one because it's a little bit easier to work through and to explain. So we have the F value equals between groups variance divided by within groups variance. Let's talk about what those terms mean. So follow me on the logic of what we're doing here. So if we have a large number on the numerator, the between groups variance, the between groups variance is how different all of these groups are from the overall group mean, the grand mean essentially. If we can show that that's a very large number, meaning there's a lot of difference between the groups versus a fairly small number on the denominator, which is within groups variance, and that is basically just variance within each group that's due to random chance. If we can show that the numerator is large, the denominator is relatively small, meaning the overall F statistic will be large, then what we've shown is that there is significant, or I should say there are significant differences between the groups. And that's how we use this to justify rejecting the null hypothesis that there are no differences in groups. So between groups variance is the average squared difference between the sample means and the overall, also called grand mean, whereas the within groups variance is the average squared difference between the scores in each group and the group mean. And we'll walk through each of those in a second. The grand mean, which again is a new thing, is all data points from all conditions or samples added together and divided by the combined sample size. So it's not just the mean within each different group, it's the mean of all of those groups combined. And I know this is all kind of confusing. I think it'll make more sense if we just run through an example of hypothesis testing using a one-way ANOVA. As always, step one is the state hypotheses. So the null hypothesis in our example is going to be the population means in terms of the satisfaction ratings of students using paper, standard electronic versus interactive electronic texts are all equal. That means that in none of those cases will have a significantly higher or lower satisfaction rating among students. So you can see that population mean for each of those conditions should be equal to each other. Our alternative hypothesis is that at least one of those population means for satisfaction ratings is different from the rest of the format populations. We don't specify exactly which mean we think will be different, but it's at least one of the means could be different, which means potentially that all of the means are different, but we haven't actually stated that. This is kind of the most basic form of alternative hypothesis you can do in a one-way ANOVA. Step two is setting our decision criterion, which we will of course use an alpha level of 0.05 or 0.050. Those are the same thing. All right, in step three, we would actually collect sample data. So we would have, in this case, 30 students from each of those three textbook groups. Let's say that we found a mean satisfaction rating on a scale of 1 to 10 for the just paper version of the textbook of 4.17, for the standard electronic version of 5.33, and the sample mean satisfaction rating for the interactive electronic is 7.83. We can also calculate the grand mean, which is going to be 5.78, and that's represented by X bar total or X bar grand, sometimes you'll see. Note that sometimes you could just take the average of each of these three samples, 4.17, 5.33, 7.83. If you take the average of those, it does equal 5.78, which is our grand mean. But that only works if you have even sample sizes, which we do in this case. But that's not always how it works. So in most cases, you'll want to actually add up each of the individual data points for all of the samples and then divide by the total sample size. And let's imagine we also calculated the sums of squares for each of these three groups to be 53, 75, and 75. So in step 4, we've got to calculate our statistics. And again, the overall F statistic that we're trying to calculate uses between groups variance and within groups variance. And this is how we take the three group means and basically turn it into two different kinds of variance that we can actually handle with a single, to end up at a single value. Our between groups variance is the sum of squares between divided by the degrees of freedom between. we've already looked at degrees of freedom between, but we'll do this here again in a second. The within groups variance is sums of squares within divided by degrees of freedom within. And it's going to take us quite a bit to get all of those numbers. And a quick note here that between groups variance is also called mean square between, which is denoted as MS between. And within groups variance is also called mean square within. And that'll make sense as we're going through the actual calculations, but if this pops up in your book, just don't be confused by that. All right, first let's try to calculate the between groups variance, which is also called the mean squared between, and that is equal to sums of squares between over the degrees of freedom between. Sums of squared between, basically you have to multiply the sample size for a group by that group's mean minus the total mean, the grand mean, and square that number. Then you add each of those the three samples together. We'll show you that on the next slide. Degrees of freedom between are much easier. You just take the number of groups and subtract 1. So what that's going to look like for us is basically you have 30 people in each of these groups. Then you multiply that by the sum of those differences of the group means and the grand means squared. So you'll end up with, in our case, 30 times 2.59 plus 0.20 plus 4.20 gives us a grand total of 209.7 as the sum of squares between. Now note that this works only because we have even sample sizes in all three of the groups, so you can just take 30 and then multiply it by these. If you had different numbers of people in each of the samples, you'd have to calculate those separately and then add them together to get the sums of squares between. Meanwhile, our degrees of freedom between is much easier. We just take the number of groups or conditions or samples, in our case it's 3 of them, subtract 1, and we get degrees of freedom between to be 2. So ultimately our mean squares between is going to be 209.7 divided by 2, which gives us 104.9, which is the same thing as the between groups variance. So we've got one part, the numerator, for our F ratio. All right, now we got to calculate the within group variance, which is also known as the mean squares within. Mean squares within is calculated by taking the sums of squares within and dividing it by the degrees of freedom within. Breaking that down a little bit further, the sums of squares within is literally just the sum of the sums of squares of each of the groups. You can see that you basically take each raw score from each person in a particular group, subtract their group mean from it, square it, and then add those together, right? So that's the sums of squares for each of the groups, and you just add up each of the sums of squares. The degrees of freedom within we saw earlier, you can calculate that by the number of people in all groups combined minus the number of groups. So let's imagine that we already had the sums of squares of each of the 3 groups. We get 53, 75, and another 75. If we just add those sums of squares for each of the groups together, we get the sums of squares within of 203. For the degrees of freedom within, you take everybody from all 3 of the groups combined minus the number of groups. So this is 90 people in the entire study, basically. Minus 3 will give us 87. If you divide then the sums of squares within 203 over the degrees of freedom within of 87, you get a mean squares within of 2.33. So now finally we have our between groups variance and within groups variance, or same thing as saying the mean squared between and mean squared within. We can finally calculate the F ratio, which is the F test statistic. So we've got 104.9 divided by 2.33, which should get us 45.02. That is our F statistic, our F ratio, our F test value, all those things. But in order to know if the F statistic was significant, we have to compare it to a critical value of F. And you look that up in a table, right? So the appendix of your book also has critical values for the F distribution when alpha is equal to 0.05. But you need to know both the degrees of freedom between and the degrees of freedom within terms to figure out what's the critical value of F. You'll see on the table that across the top, it's the degrees of freedom for numerator, which is the same thing as saying degrees of freedom between. And on the kind of y-axis, it's the degrees of freedom for the denominator, which is the degrees of freedom within, right? For our particular sample here, we were looking for a degrees of freedom between of 2 and a degrees of freedom within of 87. So across the top, degrees of freedom for numerator is 2. On the side, degrees of freedom for the denominator is going to be 87. Unfortunately, there is no value that's particularly close to 87. So we can go with the value of 120, which is actually a bit more conservative. In reality, you'd probably want to look this up online to see what the exact F critical is, if 87 is sort of in between the two values that we see of 60 and 120. But anyways, it's going to be something like, it'll be a value between 3.15, because that's degrees of freedom of 60 within, and 3.07, which is degrees of freedom of 120 for degrees of freedom within. So it's going to be somewhere between that. Anyways, we'll go with 3.07 here. So if we draw this out, we get an F distribution where the F critical that we just found was 3.07, and that basically sets up the critical region to the right of that. The nice thing about the F distribution is you're only ever worried about the right side of the distribution, essentially. Well, our observed F statistic was 45.02. That's a huge F statistic, right? And so it's way, way to the right of the F critical value, meaning that we know our observed F is going to be in that critical region, and therefore we can reject the null hypothesis. So we know we can reject the null hypothesis that all sample means are equal. In other words, that there's no effect of the text format on satisfaction in the three groups, meaning no students on average were any more excited about one form of the text than another. And therefore we conclude that at least one of the students' satisfaction means is significantly different from the others, okay? Because we rejected the null. So we are going to accept the alternative that at least one of these student satisfaction means from one of those three groups is statistically significantly different from the others, and maybe they're all different from each other. But we don't actually know. In one way ANOVA, the hypothesis testing only gets us to this point. It just says, okay, well, we rejected the null, so now we know that at least one of those means is not like the others. So if we've found significant differences between the group means, then we can move on to post hoc tests. If you did not find significant differences in group means and you fail to reject the null, then you don't do this part because you're just done. It just means that there's no real treatment effect. There's no real difference between each condition, so you're just done. But if you do find significant differences, meaning a significant F statistic, then you want to move on to post hoc tests. And basically what this does is it just breaks down the differences between samples or between conditions into pairwise t-tests. So now we can actually see if each pair of means is significantly different from each other. The problem with this is it actually increases our chance of getting a type 1 error, because every time you conduct a statistical test with an alpha of 0.05, that means that there's a 5% chance that you rejected the null when you should not have. So there's a 5% chance that you said these are significant results when actually there are not. And because we're going to be making a lot of pairwise comparisons, that increases the likelihood that we are making one of these errors. So we have to find a way to mitigate that or account for that. Now there are a number of different pairwise t-tests that you can run to figure out which of the two group means at a time are actually significantly different from each other, if any. You only do this, right, if the omnibus ANOVA is actually significant in the first place, and then you want to break it down to see, well, which of the group means are actually different from each other. And a common type is called the Bonferroni test, a pairwise test that is it's very conservative, meaning that it actually reduces the chances of making a type 1 error, which is really nice. It also, though, makes it more difficult to find significant differences in means. So it's a little double-edged sword there for researchers. There's also a very common post hoc test called Tukey's HSD, honestly significant difference test, which is similar to Bonferroni, but it's not as conservative. So it increases the chance you'll make a type 1 error, but it also makes it easier to find significant differences among group means. I thought this would be a cute image to end on. In the whole scheme of things, are we really so different? And of course, the cold calculating statistician's answer would be absolutely. You are all statistically significantly different in terms of your means. Obviously, we'd have to run an ANOVA to see if that was actually true, but all these populations look pretty different to me. Anyways, I hope you have a great day, and I will see you in the next lecture.